So I will talk about QED in the magnetic field, and as you'll see, this is an interesting kind of strongly interacting field theory where a lot of ideas about symmetries and symmetry breaking and anomaly matching play out in an interesting way, but we can also do concrete calculations. So this will be mostly based on these two papers that I wrote with collaborators in the past year. The first one is with Ryan Thorngren, who's also part of this collaboration, and former UCLA postdoc, Pierluigi Nero. And the second paper is about magnetic fields with Juan Maldacena from the summer. And there's also some related work that I probably won't have time to mention. So let me give some kind of general comments about gauge theories in magnetic fields before we get our very concrete example going. Gauge theories occur all over physics. They occur in the standard model of particle physics. They occur in condensed matter physics. So that's why they are at the core of what we study. And in particular, almost all physical theories of interest in some way or another have fermions in them. And fermions and magnetic fields interact in a kind of famously interesting way. And that leads to all sorts of beautiful physics. And in particular, there's been sort of a long-standing, many decades kind of lore that's built up that if you put gauge theories with fermions in a very strong magnetic field, that should make them do something interesting. And one of the things that's being proposed as being kind of a generic thing that happens is that it catalyzes some sort of symmetry breaking, spontaneous symmetry breaking. This goes under different names in different kind of parts of the literature, but in kind of quantum field theory, it's usually called magnetic catalysis. And the idea being that the magnetic field sort of catalyzes or helps the symmetry breaking along. And one of the reasons that that's interesting is that one of the kind of complicated, strong coupling, non-perturbative things that we would like to understand about many gauge theories is if and when they break symmetries in the vacuum. And the idea is that maybe this becomes a kind of more tractable thing once you put a magnetic field. So that's one of the reasons we would like to understand it. And of course, we would like to understand it in a kind of rigorous and controlled way without using kind of hand-wavy approximations. And then kind of figure out what we learn about gauge dynamics in this way. And even though many of the examples we're interested in, like the standard model, are in 3+1 dimensions, today I'm going to focus on a very tractable, simple 2+1 dimensional example that will kind of display all of these features. All right, so here's the model that I'll describe. It's quantum electrodynamics in 2+1 spacetime dimensions. We have a photon here. F mu nu is its field strength. And we have a bunch of massless fermions, psi I. And I is a flavor index that tells me how many fermions I have. It runs up to some number NF. And for the purposes of this talk, except for some comments I'll make on the last slide, I'm interested in studying a version of this theory that effectively doesn't have a Chern-Simons term. So I want a theory that preserves time reversal symmetry. That's what we would normally call QED. And because of the famous parity anomaly, which I'll say a few more words about, this requires the number of fermion flavors to be an even number. All right, very good. So A, as I already said, is a U1 gauge field. More precisely, it's actually a spin-C connection because it gauges fermion number. And that means that this theory is actually what we'd call a bosonic theory. It has fermions in the Lagrangian, but it does not have any fermionic gauge invariant local operators. They're all bosons. And we'll see that play out explicitly later. Okay, so in principle, you could study this theory for any even number of flavors. And the theory kind of has different regimes where it behaves in qualitatively different ways. I'll say something about that later. The minimal case that I'll spend most of my time on is the two-flavor case. And then we'll say something about more flavors later. So in 2+1 dimensions, the gauge coupling E, or E squared, has dimensions of mass. Yeah, there's a question, Dan.
States of even charge or bosonic and odd charge or fermionic.
That's
Not
exactly
that it's enforcing that there are no fermionic states.
There are no gauge invariant fermionic local operators. Okay, so if you make a point operator, which you could think of as a state on a two-sphere,
Yes.
then that would not be a fermion, right? That would not have. That would only be an integer spin operator.
There are fermionic states.
There are fermionic excitations in this theory, but they would have to be attached to a line defect, so they would not be local operators.
Thanks.
Yeah. And that's exactly the same in four-dimensional QED as well. All right, so the Maxwell gauge coupling here is strongly relevant. It has mass dimension, unlike in four dimensions, and that means that this theory, although it's abelian, is already strongly coupled. So it's a sort of baby version of a strongly coupled gauge theory that we would like to understand. And the theory is weakly coupled in the UV above this scale E squared, but it becomes, in the vacuum, it becomes strongly coupled below this scale. So E squared is the strong coupling scale of this theory. Okay, so let me say a few comments about time reversal and the parity anomaly, which will be important in a technical sense later. So I want to explain a little bit where the statement that the number of flavors is even comes from, but in the course of doing so, I will give a presentation of the theory that will be kind of technically useful. And so even though I said I wanted to study the theory without a Chern-Simons term for the gauge field, let me put a Chern-Simons term in the Lagrangian and call the level K bare, right? And the statement of the parity anomaly is that if you do the fermion path integral over the psi's, then effectively each of them generates a half integrally quantized shift in the Chern-Simons level. That half integer could be either positive or negative, and which sign you pick is actually ambiguous. It's a regulator-dependent thing. The statement of the anomaly is that this is a half integer, which means you cannot make it zero by adding a properly quantized Chern-Simons term here. And there are different regulators that will lead to different quantum shifts from the fermions and therefore require different choices of K bare to make the theory time reversal invariant. If you choose, as people sometimes do, a flavor symmetry preserving regulator, that means you treat all the psi's democratically, then they all contribute with one side, let's say plus. So the fermions will shift the effective Chern-Simons level by plus NF over 2. And that means that if you want the total quantum Chern-Simons level to be 0, which is what you care about, then you have to tune K bare to be minus NF over 2. Okay? So that's one presentation of this time reversal symmetric theory. And that's the one that I'll use later in the talk. There's a different presentation where you do not treat the fermions democratically, but you have a K bare which is 0, and you can do that by giving half of the fermions plus sign masses and half of them minus sign masses. So that maintains a manifest time reversal symmetry, so that K can be 0 throughout, but it obscures the flavor symmetry a little bit. And since we care about the flavor symmetry and its breaking and its anomalies, I actually want to keep the flavor symmetry manifest. Okay? Very good. So given that I've set up my theory so that it has time reversal, what are the other symmetries? Well, there is a zero form symmetry here, which is an interesting combination of the SU2 flavor symmetry that just rotates the fermions like a doublet. So I'm considering here the minimal two flavor case, so these psi's rotate like a doublet of SU2. The U1M symmetry here is the magnetic or monopole symmetry. And the current associated with this symmetry is just star F. So this is the kind of magnetic flux, if you wish. And operators that carry magnetic flux are called monopole operators. We'll discuss them on the next slide. Ordinary operators, like just polynomials in the fields, do not carry any monopole flux. And they're the kind of standard gauge invariant polynomials in the size. Here's two of them. Here's a SU2 singlet. Here's an SU2 triplet. And they all transform in integer spin representations of SU2. All right. As we'll see, the monopole operators, because of this quotient, can also transform in half integer representations. Sorry? Where does the mod Z2 come from? So we'll see it here. So as far as if you don't have monopole operators, you just delete the U1M and you take the Z2 quotient, and you just get SO3. And that's the statement that these kind of non-monopole operators are in integer spin representations. But when you look at the minimal monopole operator, we'll see that it transforms like a doublet. So let me just remind you about monopole operators, if you're not immediately familiar. So monopole operators are operators that are defined by kind of a disorder type construction where you drill a hole at a point x, and then you put some quantized amount of magnetic flux on the sphere that surrounds this point x. And this flux Qm is precisely the charge under this U1 monopole symmetry. All right, and in free Maxwell theory, the monopole operators are easy to describe explicitly because you can dualize the photon to a compact scalar, sigma, which you can think of as a Nambu-Goldstone boson. And the monopole operators are the exponentials, the vertex operators of this sigma. So in this case, they have a kind of pretty explicit presentation. But in general, if you have charged matter fields, you cannot use this dualization to the free photon, and you just have to use the kind of disorder prescription. And in QED with fermions, with massless fermions, famously the fermions have zero modes in the presence of the magnetic flux. And those zero modes dress the monopoles, essentially because you have to impose Gauss's law. And that means, for example, that if you take the minimal monopole operator of magnetic charge 1, it gets dressed with a single fermion zero mode, but the fermions are doublets of SU2, and therefore this monopole operator is a doublet of SU2. So that's a situation where you get a fundamental of SU2 and a monopole operator of unit charge, and that's why you have the Z2 quotient. So this Z2 selection rule is respected by all the monopole operators. Yeah, and the fact that the global symmetry of the theory is really U2 with this Z2 quotient is partially responsible for it having certain anomalies that would otherwise not be there. All right, so let me discuss them. If somebody over here raises their hand, please just shout because I don't see you. All right, so we have this U2 flavor symmetry, and as I emphasized, I also have time reversal because I tuned the Chern-Simons term to 0. And in this theory, there's a kind of parity type anomaly for those two symmetries. There's a mixed 't Hooft anomaly between U2 and time reversal. And an easy way to characterize it is using anomaly inflow. So if you put a 4-manifold whose boundary is the three-dimensional space where the QFT lives, then this anomaly is described by the second Chern class of the U2 background bundle. And in principle, you can write this term with an arbitrary coefficient theta. If theta is anything random, then this is not an anomaly. And in fact, you can kind of continuously connect it to the trivial phase. But if you have time reversal symmetry, then this theta is quantized to be either 0 or pi. And in that case, theta equals pi represents a non-trivial anomaly. And if you expand out C2 in terms of the SU2 and U1 background fields, you'll find some interesting linear combination of the instanton densities for both the SU2 symmetry and the U1 symmetry. So theta so theta, in this case, the anomaly is Z2 valued. It's either there or it's not there. And you have to do a computation in some presentation to check whether it's there. So one easy way to do the calculation is you can give the fermions a certain mass, which breaks the SU2 to its carton, and then the symmetry is only U1 times U1. You can essentially give them time reversal preserving Dirac masses, so that one fermion flavor gets a plus mass and one gets a minus mass. And the remaining theory has U1 times U1 mod Z2 symmetry, but the anomaly survives under this breaking, under this deformation, precisely because of the Z2 quotient. And that means you can actually compute it in the large mass phase at weak coupling. So it's an anomaly that's entirely matched by the kind of Maxwell phase that you get even when the fermions are very heavy. And then it reassembles into this non-abelian thing when you go to the massless point. So that's one way of computing the anomaly.
What is the answer?
Oh, the answer is that theta is pi. Sorry. Yes, it's there. The only alternative would have been that there's no anomaly whatsoever. Yeah. I misunderstood. I thought you were asking how you actually convince yourself that theta is pi. All right. Very good. So there's a lot of fun things to say about the gauge theory just in the vacuum. This theory is a strongly coupled theory, and we're entitled to try to figure out what it does in the vacuum, and that's an interesting story. But I'm going to sort of turn this talk around so that I first talk about some limit of the theory that is actually weakly coupled, where we'll be able to kind of really get our hands dirty and explain what the theory does. And then we'll kind of extrapolate to the strongly coupled regions, and I'll tell you what I think the theory does there. All right. So, the theory has a strong coupling scale, which is set by E squared. And in general, when you sort of probe the theory at sufficiently high energies compared to E squared, you have some RG-type intuition that perhaps you're entitled to kind of compute certain quantities in a weakly coupled description if you ask the right kind of high energy question. And it's not always clear what question constitutes such a reliably answerable question. So we would like to understand whether turning on a large magnetic field in this context constitutes such a question. So the hope is that if the magnetic field is sufficiently strong, this makes the problem more tractable. It's not quite true, as you'll see explicitly, that you get a completely weakly coupled problem, but you certainly get a simpler problem that can actually be solved exactly in this case. So that's what I'm going to explain. But it's not true that you simply land on a perturbative problem. There's going to be a sort of strongly coupled subsector of this new problem that we're going to have to figure out how to solve. And we're still going to end up being able to solve it because this parameter is small, but ordinary perturbation theory is not going to be enough. All right. So what happens, of course, if you've thought about magnetic fields in any context, is that if the magnetic field is very big, then the fermions kind of get broken up into Landau levels. So these are Dirac fermions, so the Landau levels are relativistic. They are labeled by an integer n, but the quantized energy of each Landau level doesn't go linearly in n. Like in non-relativistic quantum mechanics, it has a square root in it. So the gap between adjacent Landau levels is of order square root of b, but it's not quite constant. And if you make b enormous, and you ask questions at energy scales below b, then you're entitled to sort of forget about the higher Landau levels and to only restrict to the lowest one. And one interesting feature of Dirac fermions, relativistic Dirac fermions in a magnetic field, is that it has precisely 1 zero energy Landau level. So when n is 0, you get precisely 1 Landau level of 0 modes. You can think of this as some kind of souped-up version of the 0 modes that were responsible for giving the monopole operator its fermion quantum numbers. In that case, there was only 1 0 mode. Here, there's an infinite number of 0 modes, roughly speaking, proportional to the magnetic flux through the two-dimensional plane that we're studying. Yeah?
A background, or is dynamical here?
In this theory, the U1 gauge group is dynamical, so this is a dynamical gauge field.
So B will be integrated over?
Yes, B will be integrated over, but we are entitled to fix boundary conditions, right, such that the magnetic flux through space is some constant number, because the magnetic flux is a conserved quantity in this theory. It's the kind of U1M symmetry, the U1M charge. So effectively, studying the theory in a magnetic field means you're fixing a certain large U1M charge sector to study.
You're essentially integrating around some side of
Right, I'm forcing myself into the subsector with a certain magnetic flux, and the dynamics cannot kick me out of that subsector. Right, and I'm going to initiate the analysis by assuming that I have a uniform magnetic field, and I'm going to start by looking at the free fermions in that uniform magnetic field, and then we'll add the gauge interactions. So that'll be a controlled thing to do in this limit where B is much bigger than the strong coupling scale. Very good. Okay, so the 0 modes have a very simple description, right? So when you want to find the zero energy solution of the Dirac equation. You can just do it explicitly, or you open Landau and Lifshitz, and it's written there. This is what they look like. I mean, the sort of spatial part looks exactly like a non-relativistic Landau level wave function. I'll have a few more things to say about it on the next slide. And then the one noteworthy feature here is that the spinor structure is very simple. Basically, these fermions are completely polarized in one direction. And the fact that this zero energy Landau level exists in the first place is a kind of conspiracy between the orbital energy of the Dirac electrons and their Zeeman energy, which comes from their G factor. The fact that Dirac electrons exactly have G equals to 2 leads to a cancellation that enables this exact zero mode. Very good. Okay, so then if you take the Dirac field in the lowest Landau level, you just expand it like you would any free field in solutions of the Dirac equation times quantum mechanical operators. And here the quantum mechanical operators are just functions of time, because I've already solved for the wave functions in space. And so these are going to be really quantum mechanical fermions, right? 0 plus 1 dimensional fermions, but there are going to be a lot of them. And they're labeled by a continuous parameter Q, which runs over the reals, which labels this huge degeneracy of states in the Landau level. So let me say more about that. So for each fixed label Q, right, we have 2 zero modes because we have 2 flavors of fermions. Every single psi and psi bar pair, when you quantize it, leads to a 2-state system. So this leads to an enormous degeneracy in the lowest Landau level. And roughly, in order to figure out what the degeneracy is, right, you have to figure out how many values this index Q takes, and there's kind of many ways to see that. But what you end up finding is that when you put space on a manifold with spatial area A, then the number of states goes like B times A divided by 2 pi. So you can put it on a torus, you can put it on a sphere, you can put it whatever you want. If you assume that space is kind of cut off in some sense, then this is the number of states. All right? And that's just the number of zero modes. And then when you quantize them, each of them gives rise to 2 states. So you actually get an exponential degeneracy in the lowest Landau level. Right. So exactly how these states are labeled depends a little bit on the choice of gauge. This is kind of a standard thing. Here I'm using what's called Landau gauge, which is a gauge in which the y momentum is diagonalized. So you can think of the label Q literally as being the momentum in the y direction. But you also see here that there's a Gaussian that's centered on the point Q. So you can equivalently kind of think of Q as being the position in the x direction. Right? Because x and y translations don't commute in a magnetic field, that is responsible for this structure. And you see that the Gaussian is localized on the length scale of order 1 over root b. All right? So if b is very big, this is a very sharply peaked Gaussian. Okay. So I already said this, but when you understand how big this Hilbert space is, right? You have a free fermion problem whose Hilbert space has dimension 2 to the n, and you see from this that n is the area of space. So this is a highly, highly degenerate problem. So as is familiar from the quantum Hall effect and all the literature of interacting electrons in magnetic fields, this is the 0th order reason the problem is hard. So we have to immediately sort of be wary of this fact. Even when we turn on small interactions, this leads to degenerate perturbation theory. So thankfully, we can avoid this issue or sort of not even encounter it, because the interactions that we will encounter are actually very special, much more special than kind of generic interactions that one would study in the context of the quantum Hall effect, let's say. And the reason is because we're studying this very clean relativistic quantum field theory without any kind of extra junk in this high magnetic field limit. And because I'm assuming that B is much bigger than E squared, right, I'm in the regime where the gauge theory itself is still weakly coupled. So even though the fermions have this highly degenerate lambda level, the interactions that I put on top of that at the scale root B are actually very weak. And to lowest order, you're entitled to just take into account kind of tree-level photon exchange. So basically just the tree-level classical Coulomb interactions. And when you integrate out the photon at tree level, you get a Hamiltonian, which is the usual Coulomb Hamiltonian, which is proportional to E squared. And then it has a charge density interaction with a 1 over P squared that comes from the free photon propagator. Okay. And this charge density is, of course, the charge density of the fermions in the lowest lambda level. There are, of course, higher order corrections. You can integrate out things at loop level. You can integrate out the higher lambda levels. But those are all suppressed by this ratio E squared over square root of B. So what this small ratio buys us is that we're entitled to only focus on the lowest lambda level with this interaction and neglect the higher order terms. So one thing that's worth noting, especially if you're a relativistic person, is that this photon only couples to the charge density. And that's because the free fermion problem in the lowest lambda level, at least in first approximation, does not have currents. It only has densities in it. So that means that these photons cannot couple to the transverse components. Sorry, the electrons cannot couple to the transverse components of the photon. And effectively, they only couple through A0. That's what leads to this simple Coulomb interaction. But that doesn't mean that such interactions are not present. They are, in fact, present. They're just a little bit suppressed in a kind of effective field theory sense. And later, I'll show you explicitly where these kind of interactions come back. OK. So there are a number of reasons to be kind of worried about this problem. One is the one that I already mentioned about highly degenerate perturbation theory, which is always present in the lowest lambda level situation. A different way to present why this is, in general, a hard problem is to kind of do power counting in the conformal field theory sense. So these psi's that are the quantum mechanical zero modes in the lowest lambda level, they just have first order actions in time, right? So they're really quantum mechanical fermions. And so you should power count them as if they were quantum mechanical fermions. And that means they have scaling dimension 0, right? And even though you will get many powers of them in this interaction, in fact, this is a 4 psi interaction if you plug in the fact that the density is bilinear in the psi's. Since psi have scaling dimension 0, this is a highly relevant operator from the point of view of the free fermion theory. So that means that even though this number is small in some moral sense, you can't do perturbation theory in this interaction. You actually have to kind of deal with it non-perturbatively. And quite amusingly, the structure of this interaction makes it possible to solve for the ground states exactly. So this is a case where we don't have any obvious approximate methods that would be useful, but there is actually an exact solution. So that's what I want to explain next. The solution relies on the special structure of the Hamiltonian that I've kind of emphasized here by writing it as J0 something and the same J0 dagger. Because you see that this structure of having something and the same thing dagger and something positive in between makes an operator that's non-negative. Right? It makes a kind of operator that's bounded from below. And in fact, it's bounded from below by 0. And that has to do with the fact that this photon propagator has a positive residue, which is dictated by unitarity and so forth. So you have here a situation where the Hamiltonian has a kind of structure which is, well, at least in my eyes, a little bit reminiscent of supersymmetry, right? It's positive, roughly speaking, because it has the form Q dagger Q, except here Q is not some supercharge like we're used to, but Q is just some other bosonic operator like J. And you have a sum of such terms. And if you know the analogy with supersymmetry, then what you should try to do is you should try to find states that are annihilated by this operator J. If you find such a state, then that state will have zero energy, and since the Hamiltonian is bounded from below by zero, that has to be a ground state. So if such a state exists, you win. But there's absolutely no reason such a state should exist, as is the case in the case of supersymmetry. It might just be that supersymmetry is spontaneously broken, and that just means that no such state exists. So we have to try to see if we can find states that are annihilated by this state. Very good. And spoiler, in this case, we will be able to find such states. It's really nice. Such states, by virtue of being annihilated by the electromagnetic charge density, have vanishing electromagnetic charge density. So these are zero charge density states. Note that the existence of local operators that annihilate the vacuum is something that's a big, big no-no in relativistic field theory. There are theorems. There's big theorems like the Ray-Schlieder theorem, and some baby version of the Ray-Schlieder theorem says that there's no local operator in relativistic quantum field theory that annihilates the vacuum. And that's roughly speaking because you have particles and antiparticles, and one of them will always act as a creation operator to create something from the vacuum. But this is not a relativistic system anymore. These fermions in the lowest Landau level, they are not full-fledged relativistic quantum fields anymore, and we will see that we can construct operators that annihilate the vacuum. Okay. So let me discuss exactly what states you find when you try to solve this equation. In order to do that, I have to, without giving you necessarily all the gory details, I have to spell out a little bit what is the structure of this operator. I already told you it was a bilinear in the fermion fields. And when you plug in the mode expansion, of the zero modes, basically you'll get something that's bilinear in the Landau level wave functions and something that's bilinear in the fermions. So this part that is bilinear in the Landau level wave functions, I've just extracted it here, and I've called it some kernel K, which depends on the momentum and also the Q and Q prime labels that I sum over. Right, because it's a bilinear operator, I have two Q labels to sum over, which is what it's a double sum. But the operator that sits inside here is basically sort of a bilocal version of the density, just psi bar psi, contracted over the flavor indices. And then there's a very important and interesting delta function here, which I'll explain in a second, which gives you -1 precisely when Q is equal to Q prime. Here I'm being a little bit, kind of intuitive by pretending that Q and Q prime are discrete labels. You can actually discretize Q and Q prime by making space compact. Before I took them to be continuous, but then I would have had some annoying delta functions and 2 pi's here that would have obscured the fact that this coefficient is literally -1. And that'll play an important role. Where does this -1 come from? Right? If you think about the microscopic origin of the current, it's just the operator psi bar gamma mu psi in the QED theory that we started with. Let me actually backtrack to that slide. All the way to the beginning, right? The current is the thing that couples linearly to A mu. So in first approximation, it's just psi bar gamma mu psi. So it should be bilinear in the fermion. Where does this offset by -1 come from? The -1 doesn't multiply any fermion operators. It's just a kind of C number. It comes from this Chern-Simons term. Right? Remember that in this presentation where we preserved the flavor symmetry, the bare Chern-Simons term was -NF/2. And if you plug in a background magnetic field, B, this part of the Chern-Simons term will become B, and that will multiply A0. So you'll get a very specific kind of Wilson line insertion for the dynamical gauge field along time, which fixes the charge density in terms of K bare, which is in turn fixed in terms of N. So that's why this constant shift is completely fixed by the time reversal symmetry of the theory. If instead you studied the theory with an actual honest-to-God Chern-Simons level, this shift here would be by some other number. And that's also interesting, and I'll try to comment on it toward the end. Is there a question? Yeah.
Wide gap here. are the states chi gapped? Or is the current can be arbitrarily soft too?
So before you add the Coulomb interaction, all states are exactly massless.
Okay.
All the states in the Lambda level are exactly zero energy. But after you add the Coulomb interaction, most of them will be lifted. As you will see, there's one soft mode that will become a Goldstone boson in the low momentum limit.
Okay.
That'll become clear once we actually solve for the vacuum.
Okay, thank you.
Yeah. But exactly, almost all these the zero energy states in the lowest Lambda level will be lifted. All right. Good. So the easiest way to analyze this equation is to first study the case when Q is equal to Q prime. That's essentially when these guys sit on top of each other, and you can analyze them one by one. And then this equation just says that the charge density in orbital Q has to be exactly 1. Okay? And since we have two fermions, right, the Fock space of the two fermions includes states of 0 charge density, states of charge density 1, where we only fill one fermion, and states of charge density 2. And this condition tells you that you have to be exactly at half filling, so that only one of the fermion flavors is filled, but not the other. So for example, what we could do is we could just put flavor number 1 in each of the orbitals. Now, if you only study the Q equals to Q prime constraint, you could in principle do different things for different Qs. But if you impose the constraint also when Q is not equal to Q prime, you will see that energetically, all of these different orbitals want to align. Okay? So what you end up with is a kind of totally polarized spin-up state, a fully aligned kind of product state, where every single orbital gets treated in exactly the same way. For example, in the case I've written here, you only fill the one fermion for every single orbital Q. And what you get is a fully aligned state which preserves translational symmetry because you've treated all the Qs democratically. The Q, remember, is basically the momentum in the y direction. So this is a translationally invariant state. But it spontaneously breaks the SU2 symmetry because we've picked a particular flavor to fill, and that translates into some particular alignment of their SU2 spins. Now, of course, you can act on this construction with SU2, and then you'll find a state that's just as good. So there's a whole sphere worth, a whole CP1 worth of ground states, which correspond to the vacua of this problem. This is for an F equal 2. Not much more. I will actually say what they do. There's a straightforward generalization of this story for higher NF. I mean, it's group theoretically a bit more involved, but there's also symmetry breaking, also ferromagnetism of the same sort. I have a slide about it, so we'll get there in a little bit. Very good. So this is a kind of fun instance where the original mechanism that Heisenberg suggested for ferromagnetism, which is Coulomb exchange, right? Fermi statistics in Coulomb exchange, kind of gets realized in this exactly solvable context, so you can really kind of see it with a naked eye. Any more questions before we move on? Okay. All right, so let's discuss a little bit the pattern of spontaneous symmetry breaking. We already said that the SU2 symmetry is spontaneously broken, right? That we've chosen a state on this CP1. And that naively breaks the SU2 symmetry to its U1 cartan. And naively, it just leads to a CP1 sphere of vacua labeled by the direction of the spin. But actually, things are a little bit more interesting because we are in a theory that also has a dynamical photon. And remember that I told you that the only thing that mattered for the electrons was the Coulomb interaction. The sort of dynamical components of the photon basically decouple from the lowest Lambda level. So on top of everything that I've said, there's also the free photon. And if you compute the charge densities in the U1m and U1f cartans, you find that they're non-zero and they're correlated in a very particular way, given by the B field, essentially. The statement that the magnetic charge density is proportional to the B field is obvious. That's just the definition of the magnetic current in terms of star F. But the fact that the cartan of the SU2 symmetry also has a particular density that's given by B follows from the fact that we have a ferromagnet as opposed to an antiferromagnet, right? All the spins are pointing in the same direction, so you get a non-zero net U1 charge. And you see that means that one particular linear combination of these two U1s will actually not be spontaneously broken, while the other one will be. So on top of SU2F breaking to its cartan, you have a further breaking of the cartans down to the diagonal. And this sort of diagonal is, in fact, fully unbroken. Now, this U1 diagonal is sort of not just a trivial circle direction that gets producted into the CP1, because the U1 unbroken direction is determined by the cartan of the SU2. It's actually fibered non-trivially over the CP1, right? So if you look at this a little bit more carefully, what you find is that the extra U1 direction that comes from the last step of this breaking chain is precisely the hop fiber of an S3, which is fibered over the sort of CP1 base that's given to you by the fermion. So the photon provides for you the hop circle, and I'll show that to you explicitly on the next slide when we dualize the photon, maybe in 2 slides. Oops. Sorry. Why is there a star? It's to invite you to ask a question.
Yes, I understand. Well, time reversal is your symmetry, right?
That star is supposed to be there because I said that the space-time symmetries are not broken, and that's basically true. The only thing is that because this is a superfluid on top of, this statement here means that this state is also a superfluid for the U1 magnetic on top of being symmetry breaking for the SU2. And you have a sort of standard thing in a superfluid where you have time translational symmetry, but it mixes with a broken U1. So there is an unbroken time translation symmetry, but it's the diagonal of UV time translations with the broken U1 magnetic. That's what the star was supposed to mean. Thanks for the question. Next time I'll put more stars. All right, so this is also, in answer to Ivo's question. Now we can discuss the energy of the low energy excitations of the model. We have a model with symmetry breaking, so we expect Goldstone bosons. And in this example, because we've essentially been able to calculate the vacuum, we're also able to calculate the spectrum of low-lying excitations, essentially using techniques that were used in the early 80s to study the Coulomb Hall effect. And what you find is that the Goldstone boson of the kind of fermionic breaking sector, the SU2 going to U1 flavor sector, is an E plus E minus bound state. It's kind of a charmonium bound state, or whatever you want to call it. And so different communities call it different things. And this 2 fermion gauge neutral bound state has a dispersion relation which on top of this ferromagnetic vacuum can be computed exactly. Roughly speaking, for the same special algebraic reasons that made it possible to solve for the vacuum in the first place. So you basically write down a 2-particle state and with definite momentum, and then you hit it with this Hamiltonian, and it just diagonalizes almost immediately. So you can compute the dispersion relation. The dispersion relation is given by some kind of incomplete gamma function or something like that. You can evaluate it completely explicitly. Here I've only written the low momentum limit and the high momentum limit. In the low momentum limit, what you find is a dispersion relation which is omega proportional to k squared. That's the kind of expected situation in a ferromagnet where you expect a kind of first order and time action for the Goldstone boson, which I'll show you in a second. And you expect this kind of non-relativistic dispersion relation. And the coefficient alpha is some explicitly calculable number in terms of our ratio E squared over B. And you see that in the limit that we're calculating, this is a very small number. But we have all the higher order terms. And in particular, we can look at the sort of high momentum regime of this dispersion relation. This is calculable for all k, including very large k. And one of the fun things that happens in a magnetic field is that large k is actually related to large physical distances in position space. So you should think of the large K limit of this dispersion relation not as some kind of high momentum limit. You should think of it as the limit where the two constituents get pulled apart and become kind of infinitely separated in the xy plane. And in that regime, they are acted on by a confining Coulomb potential. We have a dynamical photon in 2 + 1 dimensions, and that leads to a logarithmically confining Coulomb potential between the charges. And this Coulomb potential is exactly reflected in the statement that the large K limit of the dispersion relation grows logarithmically with K. So you see that these fermions are really confined. They're not free. All right. So since we were able to solve for the dispersion relations of the Goldstone bosons explicitly, we're also able to do something which typically in field theory we're not able to do, which is to actually calculate explicitly the coefficients in the low energy Lagrangian. So usually we just write the low energy Lagrangian based on symmetries, but we can't calculate the coefficients. So here we have a situation that's better because we can actually calculate the coefficients. So for the kind of SU2 ferromagnet part of the breaking, for the Goldstone boson that has a quadratic dispersion, that's the usual first order action for that. This is a CP1 sigma model where the second order spatial derivatives are here, but the time derivatives are of first order. So that gives you this dispersion relation omega proportional to k squared. And you can match the coefficients in such a way that you get the right dispersion relation. The term here is an interesting kind of topological term. It's usually called a Berry term. It's quantized in the right units, and its coefficient is entirely fixed by the magnetic field. All right, so this term is completely fixed. So one thing that's interesting is that this way of writing the Berry term immediately suggests what you need to do in order to account for the presence of the photon, right? Because we're in a theory with a massless relativistic photon. We, in fact, have spontaneously broken Lorentz symmetry, which typically is not present in a ferromagnet. And that means we can figure out how the photon couples to everything by covariantizing formulas involving B. And in particular, in this case, you can think of this Berry term as a kind of Mixture-Simons term involving B and the connection on the CP1, the Kähler connection on the CP1. And when you can covariantize that, then you figure out how the photon couples to the CP1 sigma model. And you see that when you substitute B with dA and integrate by parts, the topological current that couples to the photon is exactly the skyrmion current, the winding current of the CP1 sigma model. So here we have a situation where the CP1 sigma model by itself has a topological winding symmetry and an associated conserved current, and the photon gauges that. And that gauging of the winding symmetry by the photon is what ultimately explains the Hopf vibration of the S3 over this CP1 that I described previously. Because when you dualize the photon to a scalar, remember in the slide on free Maxwell theory, I reminded you that a free photon is dual to a compact scalar, to a Goldstone boson in 2 + 1 dimensions. And when you dualize it in the presence of this gauging of the Berry term, you get an additional shift in the dualization rule. And that shift tells you that you're supposed to replace star F with not just d chi, but d chi plus essentially the Kähler connection on CP1. And that's the thing that Hopf fibers the chi boson over the CP1 base. So when you plug that back into the F squared kinetic term for the photon, you get a quadratic action, a quadratic looking action for chi, but it has this extra CP1 connection here, which fibers it over the base, exactly with degree 1. So this is really a smooth 3-sphere. And here's a cartoon of this setup. So here we have the CP1 base. We're picking the state, which is say the north pole fully aligned up. And then we have the Hopf fiber over the north pole. And the exponential of the dual photon is one particular component of the monopole operator. Remember, the monopole operator had two components in this theory. And which linear combinations of them get a value depends on where you are in this CP1. So at the north pole, it happens to be that only M1 gets a VEV and M2 is 0. And then they mix in a non-trivial way when you act on them with SU2. All right, maybe I'll not say much more about this unless there are questions. Yeah?
Don't you also expect to have the topological term in the sigma model?
Yeah, that's the next slide. We don't just expect it, we know it. And we know it because of anomaly matching. Right. So we haven't discussed how the anomaly that I presented to you in the beginning of the talk is matched in the sigma model, and the sigma model by itself doesn't have any anomalies. And the easiest way to see this, how this works out, is to remember that the inflow action is just C2 of U2 in the bulk, right? And the sigma model is an S3, actually a squashed S3 with U2 symmetry. And when you couple the S3 target space to U2 background gauge fields, well, you can either do this explicitly if you're looking at Lagrangians in physics, or you can turn it into a statement about equivariant cohomology. But what it tells you is that if you include in the action of the three-dimensional sigma model a term involving the pullback of its volume form, right, which is a three form that you can integrate over space-time, then coupling that to background fields or covariantizing immediately leads to the C2 of U2 in the bulk, almost canonically. And the coefficients exactly match. So what you conclude from this is that if you want to match the anomaly, which has theta equals to pi, then you need this theta term in the S3 sigma model. This is a kind of completely direct way of getting at the theta term. There's also a kind of an indirect way of arguing for it, which doesn't involve any explicit matching, because remember that I told you that the photon gauges the skyrmion current of the CP1 model, but the photon is actually a spin C connection, not a U1 connection. And that fact makes this coupling of the photon to the skyrmion current slightly ill-defined. And if one defines it properly, one actually sees that such a theta term pops out automatically. It's forced on you. And it's closely related to the discussion that Dan had with Zohar and Nadi about the Hopf term. So maybe I'll just make one quick comment here for the benefit of the condensed matter audience, which is that I mentioned on several occasions, right, the parallels with problems in the quantum Hall effect, and in particular what are called quantum Hall ferromagnets. And under certain circumstances, right, one has situations in the quantum Hall effect where there is an SU2 spin symmetry that the fermions enjoy effectively in some cases where you can ignore the kind of Zeeman couplings that breaks the SU2 symmetry. There was a lot of work on this, and this is one famous paper. Modulo a few details, which I don't want to get into, the setup that they studied is almost identical to ours. But one very important difference is that if you consider electrons moving in a two-dimensional plane, they're still subject to the normal three-dimensional, 3+1 dimensional Coulomb potential. So the versions of the formulas that I used are almost unmodified, except that one has to replace the Coulomb potential, the logarithmically confining Coulomb potential that I used, with the usual 1/r Coulomb potential in 3+1 dimensions. And technically, this is a very simple change, but it leads to some very different physical predictions. In particular, it leads to the prediction that fermions are actually not confined. And it leads to a target space for the Goldstone bosons, which is not an S3, but a genuine CP1. So well, no, in my case, I have two Goldstone bosons. First of all, I have the CP1, which in some sense you should count as one Goldstone boson, right, because it's ferromagnetic. And then on top of that, I have the S1 fiber, which comes from the dual photon. In the usual quantum Hall ferromagnetic setup, you do not get the fiber. There's a kind of decoupled linearly dispersing photon, but the Coulomb interaction with the fermions does not modify the CP1 sigma model. It's actually subleading in derivative counting. Yeah. So in their story, it was very important that the Coulomb interaction is subleading in derivatives, and therefore they could basically analyze the skyrmions of the sigma model, and they had a whole story about it. And the idea was that then they would interact weakly via the Coulomb interaction. Because the Coulomb interaction is 1 power different in 3D, it jumps from being subleading to being a leading two-derivative modification of the sigma model. So that's why it can change the target space metric instead of just being subleading.
Apply this to graphene, and there's another huge difference, which is the velocity of the fermions.
Of course, that's, yeah. But for example, in the paper I cited in the beginning by Leon and friends, they considered a situation where they actually had an emergent 2+1 dimensional photon, and then it's much more similar to what I was describing here. All right, very good. So in the last 2 minutes, let me try to sketch what happens when we leave this sort of safe and nice and calculable large magnetic field regime and reduce the strength of the magnetic field relative to the strong coupling scale. Well, then we enter strongly coupled territory, and we don't truly know what the theory does there, but we can make conjectures supported by symmetries and anomalies and other consistency conditions. And the claim, based on some recent work, is that the sigma model that I presented to you in the large field regime, in the ferromagnetic case, where we could really derive it kind of rigorously, actually smoothly interpolates down to small fields, and that the theory, even in the vacuum, in zero field, is still in the symmetry breaking phase with a sigma model that looks like a squashed S3 with a theta term, except now, of course, there would not be a B field, there would not be a ferromagnetic first order term, you would just have relativistic kinetic terms for the Goldstone bosons. All right. So I just want to remind you quickly that I'm talking here about the theory with two flavors of electrons, which is a rather strongly coupled theory. The theory becomes less strongly coupled as you increase the number of electrons, and we know that for very large NF, it's actually a weakly coupled CFT, even in the infrared, where you can calculate the scaling dimensions and you can figure out what the vacuum is, and there's no symmetry breaking. Right? So the conjecture I just presented to you is the claim that for two fermions, the theory actually is not in this conformal regime. It actually breaks symmetries and flows to the sigma model. And there's some recent body of work that points in this direction. So of course, one of the questions that we would like to answer eventually is like, sort of, what's the critical value of flavors that you need to be at to go from the conformal regime to the non-conformal regime? And the evidence right now is that it should be around 4, but it's not definitive yet. Let me not get into more details about this, since I don't have a lot of time left. Maybe just because I promised Vera a statement about larger NF. If you study the theory with larger NF, I just told you that it would be a CFT in the vacuum. But if you crank up the magnetic field, it actually behaves more or less in the same way that I described in the two-flavor case. You just have more flavors of fermions, and you have a different kind of filling constraint, but you would still get a symmetry breaking kind of ferromagnetic sigma model. The sigma model would be some kind of circle bundle over a Grassmannian, whose total space would be this quotient of UN and SUN groups. And an interesting difference would be that the photon now is no longer necessarily relativistic as you kind of dial the magnetic field down. And in this case, because the large N theory is actually weakly coupled, even in the vacuum, nothing is preventing you from only exploring the small field regime. You can actually lower the magnetic field all the way to 0 and compute the properties of this state. And you find that the symmetry breaking state persists all the way down to the CFT. So it's kind of even in the regime where B is much smaller than E squared, you're still in exactly the same sigma model. And then when B goes to 0, you go to the CFT. All right. Let me briefly mention some other generalizations that we are thinking about. One thing that I briefly mentioned is you could add a Trans-Hymans level for the U1 gauge field. This breaks time reversal explicitly, and it leads to some interesting kind of modifications of the story, but ultimately the problem is still solvable, at least when the Trans-Hymans level is kind of order 1. And then the other variant that we're thinking about, which is also interesting, is what happens if you take non-abelian gauge theory like QCD, which is also time reversal symmetric, and you put it in a magnetic field for, say, baryon number. So the theory will behave in a kind of similar way, and it will again be tractable in the large magnetic field limit, and you can derive some variant of the Carl-Lagrangian and compute, the dispersion relation of pions and things like that, things that are usually difficult to do in the vacuum, and you can do it very explicitly in this setup. All right. So that's a summary, and I'm happy to take more questions. Thanks.